For this question, there are a couple of ways to approach it. We're going to start by looking at each individual free body diagram individually. So the question is asking us for the coefficient of kinetic friction. They want to know mu. So the way we find that is we set it up. So let's look at the 4 kilogram mass. Remember, we always have to draw free body diagrams of these things. The forces acting on the 4 kilogram mass would be tension, pulling it forward, and the force of friction pulling it backward. There's also gravity and the normal force. Those two are balanced. You can draw them if you want. You don't have to, but they are there, FG. Okay, so analyzing this, we get MA equals the sum of the forces. So MA equals, since we know it's accelerating this way, I'm going to make that direction positive. So it becomes T minus force of friction. And then there's a few things we don't know here. So we don't know what the tension is. And let's expand on what that means. So M is 4. So 4, and we know the acceleration actually is 3.2. So let's just plug that in. 4 times 3.2 equals T minus mu Fn. Now what we remember, hopefully, from before is that since there's only these two forces acting, it's not accelerating in the vertical. That means Fn is equal to Fg. It's one of those special cases where Fn does equal Fg, which equals mg, which equals 4 times 9.8, right? So we can plug that in. So what we have here is 4 times 3.2 equals T minus mu times 4 times 9.8. Okay, two unknowns, T and mu. So we don't have enough information. We looked at the 4 kilogram mass. We didn't get as far as we needed to get. So now what we're going to do is look at the 6 kilogram mass. And this is kind of the MO, what you're going to do. You're going to find the information wherever you can. It's that whole puzzle thing. If we look at the 6 kilogram mass, we can see that gravity is acting on it and tension is also acting on it. Now, the key here I want you to remember is that it's accelerating down. We're taking the direction of acceleration to be positive. We're doing that to link these two. Remember, they move as a unit. If 6 accelerates down, 4 accelerates to the right, and therefore we're going to make the right positive and down positive. And when we do our MA equals the sum of the forces, MA equals, now we're going to add up the forces. I'm going to remember that FG is positive, so it's Fg minus T. And that way I get my T's are opposite, equal, and opposite. And so that I know they're action-reaction forces. So this Fg is different because it is connected to this free body diagram, right? So this Fg is going to equal mg also, but that m is 6 times 9.8 because we're looking at a different free body diagram. So we have here 6 times 3.2 equals 6 times 9.8 minus t. So we can actually get an expression for t just by going 6 times 9.8 minus 6 times 3.2. And when we do that, we find that t equals 6 times 9.8 minus 6 times 3.2, 39.6. 39.6 newtons. So then now that I have that, I can sub it back into that previous equation. So let's see, take this number, sub it back into here, and solve for mu, because that's what we're being asked to find. So then up here I get 4 times 3.2 equals, now t is 39.6 minus mu times 4 times 9.8. So rearrange and solve, and I think you'll find that mu equals 0.68. Okay, no units. There is another way to do this. If you want, I can just walk you through it super fast. An alternate solution, you don't have to watch it if you don't want, but it's treating both masses as a see this blue bubble I've drawn? I'm sort of treating both masses as if they're one. And now I'm only considering the external forces. So if you think about it, that force of gravity on the 6 kilogram mass is an external force, Fg, and I'm just going to write here on the 6 to make sure I know that it's not the force on the whole 10, it's just the force acting on the 6, the force of gravity acting on the 6, because the force of gravity acting on the 4 is supported by the normal force, so these kind of cancel out, and they don't count. They don't factor into the external forces. Because they balance out. I shouldn't say they don't count, but they balance out perfectly, so I'm going to ignore them. Then also the other forces to consider are tension, but since they're inside this bubble, I'm going to ignore them. So the last force is the force of friction. I could draw it like this, but remember, this is just really a one-dimensional problem. This pulley doesn't change anything but give it a kink. So even though it looks weird, I'm going to say force of friction on the 10 kilogram mass. And I'm just going to show them as opposing the acceleration of this object. And I know this accelerates at 3.2 meters per second squared down. So now I can set up my ma equals the sum of the forces. And when I do that, I get 10, because that's the free body diagram I'm looking at, times 3.2 equals, now remember we're taking this downward direction to be positive, so it's going to be 6 times 9.8 minus mu times Fn, which is, sorry, this is wrong. This should be on the 4 kilogram mass, not the 6, not the 10. So it's going to be 4 times 9.8. And when I do that, I think you'll see that this works out to, 0.63. So, or sorry, 68. So this is another possible solution. A little bit quicker, but also a little easier to think about. All right.